Hi there. I'm going to do a problem on circular motion, and this is going to be a level surface, so horizontal circle problem about a car on a road. So our problem reads, Alexis is in her Toyota Camry and trying to make a turn off a freeway at 19 meters per second. The turning radius of the level curve is 35 meters. Her car has a mass of 1,240 kilograms. Determine the acceleration, net force, and minimum value of the coefficient of friction, which is required to keep her car on the road. All right, what do we have here? I'm going to do a top view of kind of the situation. Alexis is trying to get off the freeway and is coming off the freeway on one of these round exit ramps. It's not a ramp though, it's flat. So we've got her coming around, so she's going like this. The radius of that curve is 35 meters. Her speed is 19 meters per second. The mass of the car is 1240 kilograms. We want to know the acceleration, the net force on the car, and the minimum coefficient of friction to keep her car on the road and not sliding off. All right, picture knowns, unknown. The object of interest is the car. I'm going to do a force diagram on the car, but here's where I'm going to do it in an interesting way. You can do it all sorts of different ways, but if I'm looking at the taillights of the car, I'm looking at the car from the back side. So I'm looking at the trunk and the taillights. What would the forces on the car look like as it's going around that curve from that point of view? Well, we still have Earth pulling down. We have the surface of the road supporting the car, our normal force. And now friction is keeping her from sliding off the road. What direction would that be? If you're turning to the right, if you're making a right-hand turn, then if there was no friction, which way would you go? You'd go whoosh that way. So friction is actually keeping you going in a circle. Friction is the thing causing that centripetal acceleration. And the centripetal acceleration is pointing towards the center of the circle. So here we've got our force diagram, and the friction is pointing towards the center of the circle. The centripetal acceleration is pointing towards the center of the circle. What's next? XY chart. Again, this is just a force problem. The only addition is this idea of the centripetal acceleration. Our forces, okay, this is the direction of the acceleration. I'm going to use my standard coordinate system. X direction, I've got a positive friction. Normal force is straight up. Weight is straight down. We're done. In Newton's second law, in both directions, let's see what we've got. X net force in the y direction equals ma(y). All right, our acceleration is all in the x direction. There's nothing in the y direction, so the net force in the y direction is going to add up to 0. Add up the forces in the x direction. There's one of them. Friction equals ma. And now here, because it's circular motion, and I want to remind myself that it's centripetal acceleration, I'm going to just remind myself like that. This is the centripetal acceleration for the circular motion. Add up the forces in the y direction. I've got a positive normal minus mg equals 0. All right. So normal equals mg is one of our equations. Friction equals mac is another one. What can we do with this? Well, at this point, once I have my two equations, I usually go back and say, what am I looking for? I'm looking for my acceleration, and if I think about it, that must be the centripetal acceleration. I'm looking for the net force on the car, and I'm looking for mu. Centripetal acceleration is right there. I know mass, I don't know friction. So can I get the acceleration a different way? Well, I do have another equation for centripetal acceleration, v squared over r. I can use this. Let's see, I know v, right? Yep, I know r. Okay, I can just plug in, so it's going to be 19 squared over 35. My centripetal acceleration, if I do the math, is 10.3 meters per second squared. There's my first answer. And again, centripetal accelerations tend to be much higher than linear accelerations, so the numbers tend to be pretty big. My net force. All right, well, the net force in the y direction was 0 because there's no acceleration. So the only net force on the car, the total net force on the car, is what's in the x direction. My net force is, I can have two different things. It's either going to be the friction, or it's also equal to mass times centripetal acceleration. I don't know this, but I do know that, and now I know this. So I can figure out what the net force is on the car because I know mass, 1240, and I know my centripetal acceleration, 10.3. So my net force ends up being 12,772 newtons. So that's going to round to 13,000 newtons. Oof, that's big. Okay, well, it's a heavy car. I mean, we're talking about 1,300 kilograms here, 1,200. My last question is, what is the coefficient of friction? All right, and that is in none of these equations. What do? Well, I go to my fun equation. Anytime I'm dealing with friction, and particularly the coefficient of friction, I'm going to use the fun equation. So F equals mu n. I want to know this. I need my normal force. Got an equation for that right here. Okay, so I can use the equation N equals mg. I need to know my friction force. And the friction force, I said, is equal to MAC. So here I have an equation, F equals MAC. Okay, I can do this. Pop in for friction, replace F with MAC. That's equal to mu times the normal force, mg. And we know the mass, but the mass will cancel. So mu is going to equal the centripetal acceleration divided by the acceleration due to gravity, 10.3 over 9.8, and I get 1.05. Mu equals 1.05? Okay, so I've been saying that our mu's should always be between 0 and 1. This is a very large static friction coefficient. So is this reasonable? It seems a little high. All right, well, 35 meters for a turning radius. It's pretty tight. I mean, I would say that's close to a standard exit ramp. This right here, however, 19 meters per second, that's about 45 miles an hour. Would you try going around a flat exit ramp at 45 miles an hour? A flat, short, a small one, not a real big one, but a real small one? I wouldn't want to try it. And the reason is we need such a high coefficient of friction. This right here is why we bank turns. Because, as we're going to see with an example in class, when we bank the turn, you actually have a much higher speed that you can go safely for a certain coefficient of friction. So even though this number is greater than 1, that is a reasonable number for this because you're going to need an enormous amount of friction to go around that curve, a flat curve, at 45 miles an hour. So I think we've got this one answered, and yeah, it is big, but that's reasonable in this case. All right, I think we've got it all. Good job.